So as Emma said, my name is Cami Hurley and I'm a PhD student in the RCSI. I'm really glad to be here to talk to you today a bit about my PhD project and then about my use of Aiforia for my image analysis. So I work on HER2 positive breast cancer, which is a subtype comprising around 20% of all breast cancer cases. And treatment of this subtype has really improved in the past 20 years or so with the use of HER2 targeting agents, such as the monoclonal antibodies pertuzumab and trastuzumab, which are the gold standard when combined, as well as by the use of tyrosine kinase inhibitors such as lapatinib. However, from 35 to 50% of patients don't achieve a pathological complete response with the gold standard, and they may eventually relapse. And robust responses can also be achieved with other combinations of the HER2 targeting agents. However, at the moment, there's no way to determine which therapeutic regimen is more likely to be effective in an individual patient. So that means there's a need to identify biomarkers of response in this breast cancer subtype to improve effective treatment and reduce overtreatment. So how do we know where to look for biomarkers of response? Well, recent evidence has implicated the immune system in the form of tumor-infiltrating lymphocytes to be playing a role in HER2-positive breast cancer outcome. And we can see these here in this image with their dark staining nuclei following a hematoxin and eosin staining on a tumor. But the limitation of the hematoxin eosin technique is that it doesn't allow for the assessment of specific immune subpopulations in tumors. And we know, of course, that there can be pro-tumorigenic and anti-tumorigenic immune subpopulations. So the hypothesis is that further investigation of the immune landscape of HER2-positive patient tumors may improve patient stratification and personalization of treatment. And the aim of my work is to analyze the densities of immune and stromal cell subpopulations in HER2-positive patient tumors treated with targeted therapies to determine an immune profile associated with response. And I'm doing this by using 3-plex immunohistochemistry. So I have designed and optimized 6 3-plex IHC panels, and these are targeting a range of innate and adaptive immune cells, stromal cells, and checkpoint proteins. And these are being applied to pre-treatment biopsies and surgical resections of patient tumors from the phase 2 TCHL trial. And the workflow for each panel is pretty much the same. I optimize the IHC, apply it to the cohort, analyze the images, and then perform statistical analysis. And I'm going to bring you through the workflow today, focusing on the TLS panel. So TLS, or tertiary lymphoid structures, are lymphoid structures that form in non-lymphoid tissues under chronic inflammation, including tumors, and they're thought to be the site of the generation of an adaptive anti-tumor immune response. And they're comprised of a T cell zone, which we can see when we stain for CD3, and this contains mature dendritic cells, which we identify by staining for DC lamp, and this juxtaposes a B cell follicle, which we see here in pink when we stain for CD20. So a really important part of my work, because I'm performing so much IHC and targeting such a variety of markers, is to validate the specificity of the primary antibody to ensure it's truly binding to its target in the tissue and not other non-specific proteins. So I do this by taking a positive and a negative cell line for each marker of all of my panels, and I process the positive and negative cell line the same way that tissue and tumors are processed when they're taken from a patient before IHC, and this is to mimic the chemistry that we have for IHC in the cell lines. And then I perform IHC of the marker on the cells with the aim of having positive staining in my positive control and no staining in my negative control cell line, thereby demonstrating specificity. So for the TLS panel, I validated specificity of anti-CD3, CD20, and DC lamp antibodies. So we can see that the positive controls in red have show clear staining, and while the negative controls shown in grey don't have any staining. So then I was happy, so thereby demonstrating that they're not having any non-specific binding. So then I was happy to optimize the IHC protocol, and we do this using tonsil tissue. So it's a secondary lymphoid organ, and therefore it expresses all of the markers of the different panels. And once it's optimized in tonsil, I then apply it to test breast tumor, and we can see here the protocol is detecting the different cell subpopulations and tertiary lymphoid structure in test breast tumor. So then I applied the whole protocol, IHC protocol, to the TCHL cohort. And this is just an example of a surgical resection. And if we zoom in on some regions, we can see the different immune subpopulations and tertiary lymphoid structures being detected. So once the whole cohort is stained and scanned, the next step is AI model training and image analysis, which of course I'm going to go into in more detail. This is just to give you an overview. If we kind of zoom in on 2 images, we can see the different cell populations and TLS that are being analysed in this biopsy from the TCHL cohort. So then you can export your data and perform your statistical analysis. So now I'm going to go on to talk a bit more about my image analysis. So of course I'm using Aiforia. So why did I choose it? Darshan has touched on some of these things, but it really is just a great opportunity to be able to have access to an artificial intelligence software without having any coding or programming expertise, and it's really user-friendly software. And it being cloud-based was probably one of the biggest determining factors for me. So I can use it on my laptop and work from home. And it's an economically viable option. And ultimately, it gives us what we want, which is quantitative data and really rapidly once your model is trained. So how does it work? In very simplistic terms, the AI aims to simulate human intelligence in machines. And in order to do this, AI models need to be developed by us humans. And the models require input from us. And this is like its eyes. And then it sends information on what it sees to its computational neural network, which is like its brain. And then it gives us back an output, which are like the decisions it's made based on what we try to teach it. So here's just an example of input I've given it. So I've annotated these different immune cell populations, and I run a training and it gives me back an output. So I can see here that it's correctly learned each of the annotations that I've tried to teach it. But it really is a case of garbage in, garbage out. So you can get very accurate and powerful models, but you do have to train them really clearly and consistently from the beginning. So how do we get a clear and accurate model? So before you even start training your model, you need to think of a few things. So do you really know what you're trying to do? So what tissue regions do you want to perform your analysis in? And what cell types do you need to identify? And are you yourself able to identify these different features? So you need to review your images before selecting your training set, and this is important to familiarize yourself with the variability in the different tissue across different patients and the staining variability, and make sure you include this in your training set so that you can teach the variability to the AI as well. And this brings us ultimately then to the most important part, which is knowing your ground truth. So the ground truth are the specific features of the regions or objects that you want to teach the AI model to detect. So essentially, it's what helps you to determine a baseline for what is or isn't your region or your object. And it brings us back really to garbage in, garbage out, because if you think about it, you can't teach the AI clearly and consistently if you yourself aren't sure and clear what your ground truth is. So I'm going to focus on ground truth for cell detection today. So what you need to consider is the size of the cell, the shape, the context, and the staining pattern. And here are just some examples of the ground truths for my different cell subclasses for the TLS panel. And these are just a few examples, and you can see even here there's quite a lot of variability. So that's why it's really important that you are aware of this and include it when you're training your model. So now I'm going to switch over to the software. So here we are. Where's my mouse? Oh, there. Okay, so here we're just in the first part we see in the software. It's just recent images that I've been working on, recent folders. Then I can go into my images, which I've divided and categorized based on cohort or project. And then to train our model, we go into the brain symbol here, and we're in our AI projects. So for today, I'm using this project, just has 3 images in it, but for your cohort or for your model training, you're likely going to have more than that. depending on the size of your cohort. So before we can, so we're in here at our image. Before we can annotate anything, we need to create the tree structure so it knows what layers we want to annotate in. So we click on Edit Layers and we add a layer. So the first thing we're going to ask it to learn is going to be the tissue or the region. So in this case, it's going to be tissue. This is also where, for example, if you wanted to have your analysis in different tissue subclasses, you would put that all in here. So I've actually like organized these in a different part of the software, so you can put whatever you want in here to suit your requirements. For today, I'm just going to focus on tissue and not subdivide. Then we leave this at region because that's the type of layer it is, and then we need to click on the field of view. So the field of view refers to the size of the view that you need to see and recognize the feature clearly. So if we're too zoomed out, the AI can't clearly distinguish borders. And if we're too zoomed in, it's not going to be able to see, for example, that this is tissue. It's just going to think it's a cell. So I selected 50 for my model. So I'll put it at 50. And then we need to set the complexity. So this is what we're seeing and this is what the AI is seeing. So the complexity is how difficult it is to recognize the pattern from the rest of the image. So we want to put it kind of at the lowest complexity that we can, with it being sufficiently a mirror of this image that we're seeing. And in the early stages of the training, you don't really want to go too high in complexity because the neural network isn't so deep yet. So we're just going to leave it at very complex for now. But later on, when you're troubleshooting, if your model's having trouble with tissue detection, these are some of the parameters that you could change around. And then we're going to add the cell layer, the cell subclasses. So again, I've made these somewhere else earlier on, and I'm just going to change the colors so that they match the IHC colors so we don't get confused. And then because I want to detect these cell subclasses within the tissue layer, I select the tissue to be the parent layer to this child layer. And then because they're cells, we're looking at objects. And again, we need to set the complexity. So because I'm looking at 4 different cell subclasses, I don't want to go too simple. But again, because we're at the early stages, we don't want to go too complex either. So as we increase the training depth and we increase the annotations and iterations, we can also increase the complexity. But for now, we'll just go at complex. So then we're ready to start annotating. So we just click on the layer that we want to annotate. So we click on tissue up here, and we're just going to zoom in a bit. You can see that under the training tab here on the left, there's 2 windows. So there's the training region and training annotation window. So I'm going to click on the marker or the pencil for the training region. And the first thing we do is we draw a training region. And we need to remember that this is the eyes of the AI. Then we want to annotate within that, what do we want to teach it to be recognized as tissue? So then I just draw my annotation. So you need a good mouse for this, and you just want to be as accurate as possible. And you can draw anywhere in the back, it doesn't matter because it doesn't see behind there. So what I've done here is we have given it some eyes, and it's sending information to its brain on what we've annotated. So we want it, it's going to learn that this is tissue, and anything within the training region that is not annotated will be sent to background. So you don't want to end up, for example, accidentally with a situation like this. Because it's really going to get confused here because you're sending this to background, but also annotating it as tissue. And similarly here, you're telling it that to learn this is tissue, but that this is background. So this would be a conflicting ground truth. And it really is important, and it took me, while I knew this, it took a while for it to really click in my head that it really doesn't see the whole image. It really only sees what's within these training regions. So it's not that it sees the whole image and only uses this part to learn. It really only sees this. So that's why it's important to, oh, and if you want to delete if you make a mistake like this, you can just, for example, add on to the annotation like this. And then if you want to delete any of it, you can just use the eraser like this. Yeah, and so because the training regions are the eyes, we need to ensure that there's different types of tissue included in its training. So we're just going to draw a few more training regions and then annotation. So it doesn't really matter what the annotations look like outside of the training region because it's not counting that. And then I'm just going to move up to another part of the tissue because I know it looks different. So just that this is included. One mistake I make is actually I mix up these two markers sometimes. So this is what will happen if you mix up the two pens, like I have done a few times. So you'll end up having more conflicting ground truths because normally we draw our training region and then the annotations outside it, but here I've done accidentally the wrong way around. So you can see here, it's going to get confused. This I wanted to recognize as tissue, but at the same time I'm telling you to put this to background. So these are things to look out for when you're annotating. Of course, you want to annotate in multiple images. So here you can flick through the images, and because it's cloud-based, everything is saved as you go, so you don't need to worry about losing any of your work, anything like that. And once you've annotated enough in your tissue layer, then you can move on to annotating in your cell layer. And so you click on the cell subclass layer, and you notice the annotations for this tissue layer go away. And now we're going to annotate for cells. So I like to go to a region where, well, it's always important to make sure that you are going to a clear region and only annotate, give clear and concise annotations. But I do like to have a look around the tissue to find a good region that I want to annotate in. And then I just click on the cell type that I want to annotate. And unlike for the tissue, I actually draw my annotations first, and then I draw my training regions around them. And I do my annotations using the object sector, which we see here. And of course, we don't need it to be this big. We just want to have one object circle per cell. So here I can change it. So I use 5 microns. And this is, for example, one of the parameters that you can change later on if your model is struggling. I know for the TLS model, in the end, for the hematoxylin subclass, I ended up increasing to 7 microns, and that made a huge difference in getting the model more accurate. So I'm just going to do some annotations now. So the most important thing when you're annotating for objects is to get the object sector centered on the cell, which can be quite challenging. As we all know, most cells aren't lovely perfect circles, but you just do your best and you'll see where it's struggling after the training, and you just need to move them around sometimes for it to get into the right position. And you really only annotate what you know yourself, like what you're confident in. If in doubt, leave it out. And the most important thing, I think, for I probably said the centering was the most important thing. Another really important thing is to, in your training regions, when you have different cell types, you really want to ensure that you have multiple cell subclasses in one training region. And that's because the AI needs to see the different cell types at the same time in order to compare them and help it make a decision on what it's seeing. Just like we do all the time subconsciously. When we're looking at an image or looking at our different colors, we compare them to each other to help us make a decision, so it needs that as well. So then I just draw the training region around, and I ensure, for example, I don't have anything like this. So if I have this cell annotated in this training region, it's going to send it to background. So I either annotate it or I just erase that part. I just make the training region smaller. And then as well, what I do sometimes is after I've made 2 training regions, I actually just join them up. May as well get more cells in there for it to see them all in one go. Another feature that you can use is that because this, when you don't annotate anything in the training region, it sends parts to background. This can be really helpful for reducing your false positives. So for example, I know in this tissue that because of the way it's been processed, or it's after going into these kind of circular formation, and because I've analysed this tissue before, I know that these get falsely detected as being hematoxin. So what you can do is include these in your training regions and even draw empty training regions to send these to background. And that's really a handy way of sorting out that problem. So I'm just going to go to another region. I'm going to draw some DC-LAMP annotations, and this is a much trickier marker, so it needed a bit more work, but we got there in the end. And because DC-LAMP is our marker for dendritic cells, they're very often, of course, with our green T cells. So I like to annotate some T cells with it. And then I may as well throw in this pink CD20 because that's going to help it, because it's good to compare the pink and the brown in one training region because they're not super far away from each other color-wise. And then you just draw your training region again. And if you you need a good mouse, and sometimes you might misjudge your ability of what you can do with your arm. And if you end up needing to let go, it'll just finish itself off, and you can just start again, and it will join up like this. There. So we've done a few annotations. We're going to run a training in a minute, but before that, another important thing we can do is draw an analysis region. So we switch to the analysis tab here. So what this means is that on this image, after it's run its training, so after it's learned from the annotations we've given it, it can also analyze part of this image based on what it's just learned. So we can see in that sense how it's performing so far. So let's say I'm going to just draw a region here and another one here, and we'll see how it's doing. And I might just draw one here as well, just to make sure, for example, there's not going to be too much false positives from this part of the tissue. And then you move to the cogs, and this is where you can type the name of your model, and you select the layers that you want to train. So we need to train tissue and cell types. You put in the number of iterations. So as I said, you start pretty low, 100, 200 iterations at the beginning. And as you increase your annotations and the complexity, you can increase the iterations as your the network becomes more deeper. You click run verification, so we get our errors in a few moments. We see we're struggling, and we also click run analysis so that it will analyze these analysis regions we've drawn. And then we click on create AI model. So I'm not going to run one now, but I'll go through some results of a different training that I did in the early stages of the TLS model training. So after you've run a training, you go back into your image, and on the left here, on the right, we click on this analysis tab, and it's going to give us the results of the training and see how it got on. So it's basically going to show us each of the annotations that we've given it, how well it learned it. So we're in the tissue layer at the moment, so I can, it gives us basically the error. It's 0% for this tissue layer. So this means it's correctly learned and not having any problems with learning that this tissue I've annotated is tissue. And then I'm going to click on the cell subclass layer. So there we see everything is accurately been learned. And then in the cell subclass, we see our total object error is over 39%. So you can also click the overall object error for all images, and then you get a list of all of these here for all of your images, but I prefer to work one image at a time. It can be a bit less overwhelming maybe. So I'll just turn that off again. And we can see so that's for your overall object errors, nearly 45%. And then when we work through one image, it goes back down to 39. And your object error is a combination of your false positives and your false negatives. And you can see here which of the cell subclasses are causing maybe the most problems, or which it's struggling with the most. And here, basically, we have a list of all of our annotations, and they're sorted by percentage error. So if we click on one of these thumbnails, we can see where it's struggling in this annotation. So when the annotation, I'll just switch off the results for a second. So the empty circles are my annotations, and then when they're filled in, it's the result it's giving us. So we can see in these three, in these three cells, it's correctly learned it, no problem. And then we can see in these two, for example, that it's after detecting 2 cells instead of 1. So we've got this huge overlap. This is something that can be adjusted for afterwards. I don't worry too much about the overlap. For this cell, for example, it's a false negative, so it's likely that it's not confident enough, so you need to increase the amount of annotations of cells that look like this. And essentially getting your error rate down, so for object detection, you want it less than 7%. So getting your error rate down is essentially about going through your errors and troubleshooting. Why is the AI having a problem with this? Do I need to increase its confidence? Do I need to annotate more? Is there a problem maybe with centering? Have I given it enough context? Do I need to change the size of the object detector? And so on and so forth. So it's really important, as well as this, going through errors, to make sure you go down to the end of this list where your error percentage is reducing. So this is not only for your own boost, but also because you want to see where the AI isn't struggling. You want to see which types of cells it's detecting easily or not having any problems with. And this is because you don't want to waste time annotating it or giving it annotations for cells it has learned properly. It's just wasting your own time, but it's also going to make the model narrow-minded and overfitting can occur. So that's why it's important to go to the bottom of this list as well. You can also look at the analysis region that you drew earlier on to see another way of seeing how the model is doing so far. So this isn't the one I drew earlier, it's from a different example. So in the green, underneath, we can see the tissue detection is pretty good. And just turn that off. And you can have a look at how it's doing for the cell detection. So we can see it's still struggling with some cells. So it's just a nice way to see, as well as your error rates, how the model is doing. And there's other settings as well that you can change around in the post-processing to get your error rate down. And these are in the advanced parameters. So you can you can apply to tissue and the cell type layer. One of the things that I used is image augmentation, and this is to reduce overfitting, increase generalization, and you can increase gain values. So there's loads of things that you can do to help you get the error rate down and get your model accurate. And then once you're happy with your model, you can select it here and you can release it here. And once it's released, then we can leave the brain part of the software and go back to our cohort, back to our images. And I'm just going to show you how to apply your released model. So I'm going to show you results from the fully trained complete AI model for the TLS panel. So this has an overall object error rate of less than 2%. So what I did here, you can see that there's annotations from the pathologist. And if we click on Analyze up here, we can click Regions of Interest. And then I can draw around the annotations of the pathologist and analyze in these regions, or you can analyze the whole image if you want. Oh, and sorry, I should say, so here's where you select your model. And I'm not going to accidentally select one because I don't want to accidentally start analyzing and lose credits. So, but it's there. And then once you've run your analysis, so once you click start analysis. It literally takes, you know, a few seconds, maybe like 10 seconds or something, depending on the size of your tissue, but it's really, really quick, and which is just amazing to see when you spend a really long time training your model, that it can then work so fast on your tissue. So really the hard work is done at this point. And then you can click on the region, and it's going to show us markup of the tissue and cell detection. Just takes a second to load. I know I didn't subdivide tissue here into tumor versus stroma or normal, but it is important to have the tissue detection in any case, because I need it for measuring the area of the tissue, which I need for my density calculation later on. So I'm going to switch off tissue so we can see the cells. They're gone. Hopefully they'll come back. There we go. This is the best part, so worth the wait. So we can toggle them on and off to see how well the model has done in detecting the different cell types in this tissue. So here's our CD3 in green. So it's doing quite well. CD20 in pink. And then there's a few DC lamp here. And we can toggle those on and off. So I was really happy when with this algorithm, and yeah, so it's great. It's really brilliant to be able to analyze these multi-labeled images with this algorithm with software. I'm just going to switch back to, oh sorry, and then you can export all of your accounts and for your statistical analysis just here, and you get all of your accounts and you can calculate the densities. I'm just going to switch back to just give a summary, I suppose, of what things I did to reduce my error rate, and just reiterate that some of these things really need to be balanced when we're referring to the annotations, complexity, and the iterations. And it's really important not to overtrain your model, as I said, because we don't want it to be too narrow-minded. And just to give an overview of the training for this model, I did 21 versions, with my first version having 160 annotations and an overall object error of over 40%. And then finally, in my 21st version, I had 3,500 annotations and an overall object error of 1.62%, which I was really happy with. So yeah, thanks everyone who supported and helped me in this work, and to my funders, and of course to the patients and their families. And thanks everyone for listening today. And I'd be glad to have any discussions or questions you might have.